So now I am going to take the question number 11. The two arms of balance are of unequal length. An object when placed in the left pan of the balance weighing 4 kg, the same object when placed in the right pan of the balance weighs 9 kg. The actual or true mass of the object is this. So we can solve this question by using moment of force. So now I am going to take my case number 1. In the case number 1, suppose this is the situation. Suppose this is the fixed point, and one pan, if I consider the mass is m0, and on the right hand side if I consider the mass is m1, and the distance from fixed point is L1 from the left hand side, and from the right hand side is L2, right? And this is my case number 1. So we all know the perpendicular distance from m0 is L1 and perpendicular distance for m1 is L2. So if I use the moment of force, so we'll write m0 L1 from left hand side, and in the case of equilibrium we'll write m1 L2, and this is my equation number 1. Similarly, if I make the second situation according to the problem, so if I consider, because I am going to change, this mass is m2 in this time, and on the right hand side I am going to take m0 according to the problem, and this is my point where we have to calculate L1 and L2. Similarly, in the case number 2, we'll write m2 L1 m0 L2, and this is my equation number 2. So if I divide equation 1 and 2, so L1 L1 will cancel out, and I have m0 upon m2 and m1 upon m0 on dividing equation 1 by 2. So when I will take the cross multiplication, we'll write m0 square, that is equal m1 into m2, but I need to calculate only m0 because m0 is the true mass. So with the root m1 into m2, the value of m1 is 4 kg as per the question, and m2 is 9. So on solving we'll get 6 kg. So this is the value of true mass of the object. So we can say my option number 2 is correct. So let's move on question number 12. So now I am going to take question number 12. Two discs are mounted on frictionless bearing on a common shaft. Okay. The first disc has rotational inertia I and is spinning with angular velocity omega. The second disc has rotational inertia 2I and is spinning in opposite direction. So you have to be very careful, in opposite direction, with angular velocity 3 omega as shown in figure. Two discs slowly force towards each other along the shaft until they couple and have a final common angular velocity of this. So by this question or by this discussion we can conclude that there is no external torque, because if I take whole arrangement as a single system, so we can say there is no external torque. If there is no external torque, we can apply the law of conservation of angular momentum. So first I will write initial angular momentum and final angular momentum according to the law of conservation of angular momentum. This is the total final angular momentum, and Li means total initial angular momentum. So I am going to write, because you know angular momentum is given by I omega, where I is the moment of inertia, omega is the angular velocity. So I am going to write first the value of total initial angular momentum. So that is 2I is the moment of inertia into angular velocity is 3 omega, but you have to be very careful regarding the direction, that is anti-clockwise as per the question. And because I need total initial angular momentum, so we'll add them. For the first moment of inertia is I, angular velocity is omega, but in this time the direction of this is clockwise, so we'll use minus sign will be here. And now I am going to take total final angular momentum. So total inertia is 2I plus I into omega c. Omega c is the common angular velocity. So now I am going to solve this. So we'll get 2I into 3 omega minus I omega, and that is equal 3I into omega c. So when you will solve, 3 2 ja 6 minus I omega, will get 5 omega, that is equal 3 omega c, because I will cancel out. So I have the final common angular velocity is 5 by 3 into omega. So this is my final value. So we can say my option number 1 is correct. So let's move on question number 13. I am going to take the question number 31. Now I am going to take question number 13. From a ring of mass m and radius r, a 30-degree sector, this is the ring, and 30-degree sector is removed. This portion will removed. The moment of inertia of the remaining portion, this is the remaining portion of the ring about an axis passing through the center and perpendicular to its plane of the ring is. We know the moment of inertia of the ring about center of mass is given by mr square. And we know there will be no change in formula if shape of the ring will change. So I need only the mass. This mass is for remaining portion. So how you will calculate the mass of remaining portion? So I will use mass per unit angle. जैसे हम लोग लीनियर मास डेंसिटी सॉल्व करते हैं फुल मास के लिए, ठीक उसी टाइप से इफ आई गो फॉर mass of remaining portion, so that will calculated by mass per unit angle, that is 2 pi for complete rotation, and I need only 360 minus 30, because total angle for complete rotation is 360, but that part will remove. So mass of remaining portion will be 360 minus 30. So when I will place the value of 2 pi, this is 360 and this is 330. So we'll solve, we'll get 11 upon 12 m. So this is the mass. If I represent by m dash, so this is the value of m dash. So when I will place this value in equation number 1, we'll get 11 upon 12 m into r square, and this is our required moment of inertia as per the requirement. So my option number 4 is correct. And let's move on question number 14. Now I am going to take the question number 14. A rod is pivoted at center A. 10 Newton force is applied 4 meter from the pivot, and another force 5 Newton is applied 2 meter from the pivot point as shown in the figure. The magnitude of the total torque about the pivot is. This question is based on the application of the formula. So first I will make the free body diagram, we'll see. If I resolve the component of these two forces in rectangular form, so we'll see this is 10 sine 60, and the another component of this force is 10 cos 60. And similarly, if I go on this point, then the component of 5 Newton in negative y is 5 sine 30, and the another force is this along positive x axis, and that is 5 cos 30. So this is the forces, but I need to calculate torque. So we'll see. First I am going to calculate torque about point A. So I will write A. First I need the force and perpendicular distance. So force is 10 cos 60, and this is the line of action. If I draw a line along with the direction of 10 cos 60, that is called line of action. But I am going to calculate the moment of inertia about this pivot point, and this distance is 4 meter, and there is no confusion. This position, I mean 4 meter, making angle 90 with the 10 cos 60. So this is the perpendicular distance. So I am going to write 10 cos 60 into 4. 4 is the perpendicular distance. On solving, we'll get 20 Newton meter, and this is the torque about this point for A. And now similarly, if I go for the torque B about the similar point, so if I take this force 5 sine 30, so force is 5 sine 30, because we all know torque is calculated by force into perpendicular distance. The second requirement is perpendicular distance. Similarly, we can draw a line of action along with the direction of 5 sine 30. So now I am going to take torque for B, 5 sine 30 into 2. On solving, we'll get 5 Newton meter, because sine 30 will cancel out with 2. But now I am going to take sense of rotation by these two torque. So if I go for 5 cos 30, this force will create a torque in anti-clockwise direction, but 5 sine 30 will also create a torque in anti-clockwise direction. So for the net torque, we can add them. First torque is 20 and second is 5. So total torque will be 25 Newton meter. So my final answer is option number 3. So let's move on question number 15. Now if I go for question number 15, the moment of inertia of a uniform square plate. Plate is uniform, mass m, and h length about one of its diagonal is. So I need to calculate the moment of inertia of uniform square plate of mass m, as length a about one of its diagonal. So suppose this is the square plate and these are two diagonals. If I consider this diagonal along x-axis and this diagonal along y-axis, and perpendicular to the surface, this is our z-axis. इस z-axis का मतलब है perpendicular to the plane. And we know the moment of inertia about z means moment of inertia about the center of mass is 1 by 6 ma square, because side of square is a. So this is the basic formula, but I need to calculate the moment of inertia about its diagonal. So because here we can see that, we can say that two diagonals are perpendicular with each other. So I am going to take perpendicular axis theorem, that is IZ, IX plus IY. The value of IZ is 1 by 6 MA square, as I said, and IX is along moment of inertia about diagonal. IY is also moment of inertia about diagonal. So we'll write 2 times of moment of inertia about diagonal, that is 1 by 6 MA square. So when I will take moment of inertia about diagonal only, so that will give you 1 upon 12 MA square. So this is the final value. So we can say my option number 3rd is correct. So let's move on, question number 16.